Hello students, welcome back to our second module on chemistry, module 1.2.2, characteristics of atoms. Last time we stopped with this slide that you see on your screen now, totaling the worth in terms of chemical elements of the human body. We're going to continue by discussing what elements are made of. We're going to start by considering the atom. An atom is defined as the smallest part of an element that retains its distinct properties. For example, if we took a little hunk of copper and we broke it down and we divided that in half and divided that in half and kept going and going until we got very tiny, and when we broke it in half again, it no longer had the characteristics of copper, then the unit before that would be an atom. So an atom is as small as you can break an element and still retain the characteristics of that element. In general, we're going to learn about atoms by going over six properties or characteristics that atoms have. The first concept is that an atom is composed of three subatomic parts. If you look at that word subatomic, it means smaller than an atom, so they're very well named. You will need to know the names of the three subatomic parts, and they're what make up all of the atoms that we know of. The first of these three subatomic particles is called the proton, and this is a positively charged particle that occurs in the nucleus. And it also has mass. A neutron, as the name implies, is neutral. It is a particle that has no charge and also occurs in the atomic nucleus. The electron is the third and final subatomic particle. It has a negative charge and it occurs outside the nucleus. So I've been using the term nucleus. Let's see if we can look over here to the right here at these illustrations. This first illustration here shows the planetary model of the atom, in which the atomic nucleus has particles in the center, and the electrons are seen to orbit almost like planets around a sun, and hence the name planetary model. In fact, we know that the nucleus occurs in some configuration very close to this, but that the electrons do not occur in such a simple orbital pattern. Here is a second model in which the nucleus remains pretty much unchanged, and you see instead of having an orbit in which the electrons follow a given path, the shaded area just shows the probability of them occurring in this area. And so it's not just a simple planetary model. Although the planetary model will work great for Biology 101 for understanding what we're talking about here. Now I would like you to look at this. This is the atom is of helium, and helium has two protons. Now it turns out the number of protons is a very critical number. If you look right down here, the atomic number of an element equals the number of protons. And here I've written something very important. It is the chemical identity. So if you change the number of protons, you change the chemical identity of an atom. It becomes a different element if you have a different number of protons. So that's a key point. And you also notice that in a neutral atom that the number of protons which have a positive charge is equal to the number of electrons which have a negative charge. And so the net charge is zero. The positive and the negative charges are equal in number, and they cancel each other out. A second character, before we go on, I do want to point out that most of an atom is empty space. If the nucleus was like an orange and we set it down on a 50-yard line here, the electrons would be outside the stadium. And so the vast majority of an atom is empty space. And it is the electrons that are on the outside that determine how atoms interact one with another. And I'm not some great fan of the University of Alabama, but this is a beautiful football stadium. And so there you go. A second characteristic deals with what I just said, that the number of protons equals the number of electrons in an uncharged atom. And so a regular uncharged atom has one negatively charged electron, one positively charged proton, for a net charge of 0. Or we could look at Fe. By the way, the first one was hydrogen. The second example here, Fe, 26 electrons, 26 negative charges, 26 protons, 26 positive charges, and they cancel out exactly. And you can see here are a few other examples which show in an uncharged atom that the number of electrons are equal to the number of protons. And the number of neutrons does not affect the charge. A third important fact, characteristic of atoms, is how the electrons are configured. If it is the electrons that are determining how atoms interact, their configuration is extremely important. And in a chemistry class where you could dedicate much time to this study, we would learn in more detail the arrangement of electrons. But here we're going to simply say that electrons fill what are called energy levels or shells. And atoms may gain, lose, or share electrons to fill the outer shell. And that is the basis for all chemical reactions. Now, I would like you to remember the number of electrons that the first three shells can hold. The first shell can hold 2 electrons, the second shell can hold 8 electrons, and the third shell may hold 18 electrons, but it has a stable point at 8 electrons. Now, the electrons in the outer shell are called valence electrons, regardless of how many shells there are. As you can see just by looking at these diagrams of atoms over at the right, some atoms that are smaller, like hydrogen, have a single shell, while others that are larger may have 2, like oxygen, or you can get even larger, for example, sodium, and there are 3 shells. And we always refer to the electrons in the outer shell, whether there's 1 shell, 2 shells, or 3 shells, as valence electrons. A fourth attribute of atoms that will help us to understand chemistry is that atoms bond together to form molecules. A molecule is defined as 2 or more atoms bonded together as one unit. And this word bond, these are chemical bonds. And the atoms may be the same element or they may be different elements. For example, the first equation here shows 2 hydrogen atoms that are bonding together to form hydrogen gas. And in the second example, we have 2 hydrogen atoms and 1 oxygen atom that are bonding together to form water. And so we can see just some examples of bonding. A fifth characteristic of atoms that you need to be aware of is that they may occur as ions. An ion is an atom with a charge. That is, that the number of protons differs from the number of electrons. Recall that the number of protons is equal to the atomic number, and it defines the chemical identity of the atom or element that we're talking about. And so it's typically the number of electrons that varies. So we have a positive ion if an atom has lost 1 or more electrons. So it has more protons than electrons. And so a positive ion has fewer electrons than protons, or more protons than electrons. A negative ion, it is a negative ion if the atom has gained 1 or more electrons. A negative ion has more electrons than protons. And here we can see sodium and chlorine are some examples. And we'll return and talk about ions some more, but it's just critical to remember that the charged particles are not equal in number. So you have either a positive or a negative charge, depending on whether you have more electrons or more protons. A sixth attribute of ions is that some ions occur as isotopes. Now, the concept of an isotope, an isotope is an atom with a varying number of neutrons. In other words, you have the same number of protons in 2 atoms, but one has a different number of neutrons in another. And this might sound unusual, but most naturally occurring elements occur in multiple isotopes. So it's not an uncommon thing. For example, here is an example of 2 carbon atoms. Notice that carbon has an atomic number of 6. That's how many protons it has, because these are both carbon atoms, both carbon isotopes. They have the same number of protons, but what they vary in is the number of neutrons. And notice the one on the left is carbon 12, and the 12 refers to the atomic mass, and so that's 6 protons and 6 neutrons add up to 12. In carbon 14, you have 6 protons and 8 neutrons adding up to 14, carbon 14. And so that is the difference. We should also, at this time, when we're talking about isotopes, explore the concept of radioisotopes, or what are known as radioactive isotopes. This is where radiation comes from. And radioisotopes are unstable atoms that spontaneously decay into other isotopes or into other elements. So because they have such a large nucleus, it is unstable, and it spontaneously emits high energy particles, which is what radiation is. And if in the process of radioactive decay, losing this energy and this mass, you lose a proton, then radiation can cause one element to decay into another. An important definition in the context of radioisotopes is the concept of half-life. Now, half-life is a time. And remember, that's what it is. It's a time required for half of a sample of a radioisotope to decay. For example, if I was holding 1 gram of carbon-14, half-life would be the amount of time it would take for it to decay to where there's only half a gram. That is, half of the sample is gone in how much time. That's what half-life is. And we are using carbon as an example here because radioisotopes, of course, radiation can be weaponized in nuclear weapons and that kind of thing. But radioisotopes have been critical tools for biologists. They're used as tracers for dating, radioisotope dating, also used in radiation therapy, and many other functions in biology. So radioisotopes have been really critically important. This little table here will help us to better understand the concept of radioisotopes. I think I've tried to lay out all the important facts here for carbon-12, carbon-13, carbon-14. These are the 3 naturally occurring isotopes of carbon. You'll note that only carbon-14 is a radioisotope. The others are not radioisotopes. Notice the definition: carbon-12 has 6 protons, 6 neutrons. Carbon-13 has 6 protons, 7 neutrons. Carbon-14 has 6 protons and 8 neutrons. What would happen if we didn't have 6 protons? It would no longer be carbon. So you have to have 6 protons for all isotopes of carbon. And the number of neutrons changes. The next row here shows the atomic mass, 12, 13, 14. And radioactivity, notice that carbon-12 and carbon-13, because they are not radioisotopes, they're stable, and carbon-14 is radioactive. It is a radioisotope. Now, the next row refers to the occurrence in nature. 98.89% of carbon in the world and in living things is carbon-12. 1.11%, which you will note adds up to 100%, is carbon-13, and a vanishingly small amount is carbon-14. But the carbon-14 is enough for us to measure. We can look at the half-life. It doesn't apply, Na not applicable to carbon-12, half-life is not applicable to carbon-13, but half-life is applicable to carbon-14, this radioisotope of carbon, and it takes 5,730 years for 1 gram of carbon-14 to become half a gram of carbon-14. Now, what about the concept of carbon dating? You may have heard of that. Carbon dating is when we look at the ratio of these 3 isotopes. Notice that carbon-12 and carbon-13 remain constant, but the proportion will change as carbon-14 diminishes. And so we might find a particular sample, say of wood or something from a pre-technological building, say up at Wupaki or one of these sites, and we want to know how old that wood is. We can actually measure the proportion of carbon-14 to carbon-13 and carbon-12. Now, the younger that a sample is, the more carbon-14 there will be. And let me see if I can explain why that is. As long as something is alive, it continues to assimilate carbon-12, carbon-13, and carbon-14 in the proportions that are listed here in the occurrence row. But as soon as, say, a tree is cut down, it stops assimilating carbon-12, carbon-13, carbon-14, and the carbon-14 starts to decay. So over time, the amount of carbon-14 will diminish relative to the amount of carbon-12 and carbon-13. And it is this ratio, this comparison of the amount of carbon-12 and 13 compared to carbon-14 that tells us how old something is. Now, there are some limits on carbon dating. And one of the important ones to understand is that carbon dating cannot measure how old something is that is extremely old. If it has to go through very many half-lives, then there's not enough carbon-14 left to get really a proportion. And the carbon-14 is, for all intents and purposes of measurement, gone. And we can't measure the tiny amount of carbon-14 that remains. Remember, we started with a very small amount, and so the fact that we can measure it at all is pretty noteworthy. So if we wanted to measure something like that, something that's older than, I don't know, a couple 100,000 years, we would probably have to use a different isotope if possible. And of course, the other thing is the thing that we want to measure has to have carbon in it. I had a friend that found some horseshoes in Turkey. They're like from the Roman occupation, really interesting kind of horseshoes. And she said, well, I'm going to have these carbon dated. And I said, well, I don't think so, because they're made out of iron. They don't contain carbon. Maybe if they had some carbon in the steel, it would be possible, but not much there. So I doubt that that's going to work. So two limitations on carbon dating is that it has to contain carbon. The sample that we measure has to contain carbon, and it can't be too old. Otherwise, there won't be enough carbon left to measure. The last thing that we're going to talk about in this particular module is a periodic table of elements. This was a listing of all the known elements on a table, and this was done by the Russian scientist Dmitry Mendeleev. And he grouped the atoms according to their valence electrons. And he actually left gaps where he said there must be another element here, but it was unknown to science, and later it was discovered. So it turns out the periodic table was one of the great generalizations of science, and it really was a spectacular. It was and is a spectacular tool for science. If you want to learn more about the periodic table, you can look here at this URL here. Put that in your browser and check it out. But I won't make you do that. Here is the periodic table, and remember I told you that there are 92 naturally occurring elements. So look at the atomic number is what the elements are listed by. There's number 1, number 2, number 3, number 4, 5, 6, and you get the idea. If we go down here and we look at 92, 92 is U, that's uranium. And after uranium, 93 to 103, those 10 elements are all man-made elements, made in particle accelerators, and they exist for just milliseconds, something like that. Anyway, it's kind of interesting, but we're not going to do a lot with the periodic table of elements. But if you want to know what the atomic number is, you can always look here and figure it out. Other listings of the periodic table also list the elements. Here it just has the symbol, and it doesn't list the element. In any case, this will conclude this module, and we will continue later. Thank you.